In this session, we'll cover the neutral voltage test, which measures the voltage between the service neutral and an independent earth. Here's a reference from WPS005. If the neutral voltage is less than 6 volts, the service is okay to connect. If the voltage is between 6 and 15 volts, we need to inspect the neutral connections using standard visual checks and testing methods. If issues are found, they should be fixed and the system retested. If no issues are identified but the voltage is still high, the service may be connected, but an ISR report must be completed. For contractors, power and water will need to be informed so they can verify current on all phases of the service and possibly install loggers to monitor the situation. In this circuit model, R, Cn and RCA represent the cable resistance in the service line. RF is the fuse resistance. RA and RN are the resistances of the network lines. Transformer RT resistance is also included. The neutral voltage depends on both neutral current and neutral resistance. Ideally, the neutral voltage should be close to 0, which is true if everything is balanced. Neutral current results from the imbalance of the three-phase supply currents, IA, IB, and IC. Neutral resistance is the cable resistance in the network neutral cable from the transformer to the service point. The sum of IA plus IB plus IC is the neutral or imbalance current of the three-phase supply. Example: calculations. If we set the neutral current to 10 amps with a neutral resistance of 0.11 ohms, the neutral voltage will be neutral voltage equals current times resistance equals 1.1 volts. An important detail here: the voltage between nodes 6 and 8 is the same as between nodes 0 and 4 because no current flows through RCN and RE1. This absence of current means there's no voltage drop across these components. If neutral current increases to 50 amps, neutral voltage rises to 5.5 volts. At 100 amps of neutral current, the voltage increases to 11 volts. According to WPS 005 standards, voltage between 6 and 15 volts would require further investigation. The next steps would include visual inspection, testing the neutral integrity, conducting a voltage quality check to assess the system's condition. In this scenario, with a measured neutral voltage of 11 volts, further testing is required as per WPS 005. 1. Conduct a neutral integrity test. Use a neutral integrity meter to measure the resistance between the active and neutral lines. This resistance includes the entire path from active to neutral back to the transformer, not just the neutral resistance alone. It's the sum of RCN, RN, RT, RA, RF, and RCA totaling 0.5 ohms. 2. Estimating neutral resistance. We can approximate the neutral resistance to be roughly 1/5 of the neutral integrity test value, which gives us 0.1 ohms. Calculating neutral current using the neutral voltage, Vn, and neutral resistance, Rn. Neutral current equals Vn divided by Rn equals 11 volts divided by 0.1 ohms equals 100 amps. So what does this tell us? A neutral current of 100 amps indicates a significant imbalance in the three-phase loads. This should be reported by raising an ISR or notifying power and water if you're a contractor. Key takeaway: high neutral voltage combined with low neutral integrity resistance suggests a substantial imbalance or high neutral current in the system.